Hey guys, so this video assumes that you have already watched a video which I published earlier, which is titled Excel Interactive Loan Amortization Table, which goes into great detail about how to build a loan amortization schedule. If you haven't watched that video, I highly recommend you watch it, with the link being in the description below. In that previous video which I uploaded, I showed you how to build a loan amortization schedule using Excel's financial functions, namely the PMT, PPMT and IPMT function. However, there is one scenario where the use of these functions do not give the correct principal and interest repayment amounts, and that scenario is where you have a balloon payment at the end of the loan term and the loan repayment is being made at the beginning of each period. So to demonstrate this problem, in this scenario that we've got here, we can see that we've got a balloon payment of $10,000 for $100,000 principal loan amount, and the payment type is 0. So what this means is the loan is being repaid at the end of each period. So we can see if we go down to period 5, we can see that at the end of period 5 we have a remaining principal amount of 10,000, which equals our balloon payment amount. So this implies that the figures that we're seeing in this table is completely correct. However, in the scenario whereby we change the payment type to 1, which means that we are repaying the loan at the beginning of each period, we can see that at the beginning of the last period, period 5, the remaining principal amount is 9,523, and this does not equal the balloon payment amount. And this implies that our total repayment amount, the total principal repayment amount, and the total interest repayment amount is not correct. And the reason why it is not correct is because the PMT, PPMT and IPMT functions do not use the correct discount factor when calculating the repayment amount, so it's an actual error within the Excel functions itself. Fortunately, we can rectify this issue by building a similar amortization table like this, which no longer uses any of Excel's PMT, PPMT and IPMT function. This video will show you how you can build this table. So you might be aware of a table which provides us with the discount factors that enable us to calculate the present value of an annuity. This is the table that I'm referring to over here. So if you've got any kind of mathematical background, you might be aware of this table. So in simple terms, these discount factors that you see here within the table enable us to calculate the present value of a fixed amount of money that is paid at the end of each period for a specified number of periods. This fixed amount will represent our fixed periodic loan repayment amount. So the formula which this table uses to calculate these discount factors is given here. So it's 1 minus 1 plus r whole thing to the power minus n divided by r, where r is the adjusted interest rate and n is the total number of periods within our loan amortization table. So we need to use this formula here to calculate two separate discount factors, one when the loan repayment is at the end of each period and one when the loan repayment is at the start of each period. So let's go back to our Excel file. So if we go to this new tab over here, this new model tab, this contains the new loan amortization table that we wish to build. So what I've got here is I've got two columns, J and K. So one signifies the repayment at the start of each period, which is a payment type of 1, and the other one signifies a repayment at the end of each period, a loan repayment at the end of each period, which is signified by a value of 0. These are the values which Excel essentially uses when we use the PMT, IPMT and PPMT functions. So when calculating the annuity factor when the repayment is at the end of each period, it's very simple. We just have to plug in the relevant parameters here into the formula to generate that discount factor. So in this case it will be equals 1 minus 1 plus the adjusted interest rate, close parentheses, then to the power minus the total number of periods in our table, which is in cell E5, and then the whole thing needs to be divided by the interest rate, the adjusted interest rate. We're always using the adjusted interest rate in this scenario, in this situation. So we select cell E4 and then we click enter, and we get a discount factor of 4.33, an annuity discount factor of 4.33 when the repayment is at the end of each period. So next we move on to calculating the annuity discount factor when the loan repayment is made at the start of each period. However, in this case there will be a slight difference in how we use the annuity formula here. This is because the annuity formula calculates the present value when each repayment is made at the end of each period. However, in this case, where the repayment is at the start of each period, the first repayment will be made at the start of the first period. So this will not need to be discounted, and as a result there will only be n-1 repayments which will have to be discounted. So in this case there'll only be 5-1 periods that will need to be discounted. So when we apply the formula, we need to replace the n here with n-1 and also add 1 to the end of the entire formula to include the first repayment amount, which is not discounted. So our adjusted formula will look something like this. This is what it will look like when calculating the repayment, when calculating the annuity discount factor when the repayment is at the start of each period. So we can just plug in our parameters into this formula here. So next we'll just enter this formula into cell J3. So that will be equals 1 minus 1 plus the adjusted interest rate to the power minus, open parentheses, our total number of periods, minus 1, close parentheses. Then we need to divide this entire thing by the adjusted interest rate, and then we've got to add 1 to the entire formula, and this gives us an annuity discount factor of 4.55. Next we need to calculate the present value of the balloon payment. So the balloon payment is the lump sum amount that we pay at the end of our loan term. So when calculating the present value, we just use the standard present value formula, which is this formula here, 1 plus r whole thing to the power minus n, which is the same as 1 divided by 1 plus r to the power n. So we'll start by calculating the present value of the balloon payment when the repayment is at the end of each period. This is very simple. We just plug in the relevant parameters into our present value formula. So it will be equal to our balloon payment times, divided by 1 plus the adjusted interest rate to the power our total number of periods in our amortization schedule, and that gives us a present value for the balloon payment of $7,835. When we calculate the balloon payment's present value when the loan repayments are made at the start of each period, there'll be a slight modification in how we use this formula. The reason being is because we are repaying the loan amount at the beginning of each period, when it comes to paying off the balloon payment in the last period, this payment will be made at the beginning of period 5. So in essence we are paying off the balloon payment 1 period earlier compared to when the repayments were being made at the end of each period. So we just have to replace the n in our present value formula with n-1 instead. So we'll do equals our balloon payment of 10,000, that divided by 1 plus the adjusted interest rate to the power, open parentheses, our total number of periods in our model, which represents n, and then we minus 1 from it, and then we enter it, and that gives us the present value of 8,227 for our balloon payment when our periodic loan repayments are made at the start of each period. Next, we need to calculate the periodic loan repayment amount that we will make. So for repayments made at both the end and at the beginning of the period, this will be calculated by subtracting the present value of the balloon payment from the total principal amount and then dividing it by the annuity discount factor. So we'll start by calculating the periodic loan repayment when the repayment is made at the end of each period. So for that we'll do equals, open parentheses, our total principal amount minus the present value of the balloon payment, close parentheses, and then divide it by the annuity discount factor. Remember, as periodic loan repayments represent a cash outflow, this value here needs to be a negative amount. So we can just times it by -1 and then press enter, and we get minus 21,287. So this represents the amount that we will pay as part of our loan repayment every single period until the end of the loan term. So similarly, when we calculate the periodic repayment when repayments are made at the start of each period, we'll do equals the total principal amount. So let's first open our parentheses. It will be the total principal amount minus the present value of the balloon payment, close parentheses, divided by the annuity discount factor. And again, because it's a cash outflow, it needs to be a negative value, so we times it by -1 and then press enter, and this gives us 20,187, which represents the amount that we will pay each period on our loan as part of our loan repayment when the repayment at the start of each period. So now we'll move to our amortization table and go to cell B1, which is within our payment column, and we need to insert a formula whereby if the value in cell C6, the payment type, is equal to 1, in other words, if the repayment is at the beginning of each period, then we want the repayment amount to be equal to cell J6, because that has the value of our periodic loan repayment when the repayment's at the start of each period. Otherwise, if that's not the case, in other words, if the payment type is 0, whereby we are repaying the loan at the end of each period, we want the repayment amount to equal the value in cell K5 instead. And then we close parentheses, and then we want to fix all of our cell references here so we can drag the formula down. So let's do it one by one. So let's fix that, and then we can fix these two together. And now we can just enter and then drag the entire formula down so that the entire column is populated with the right repayment figure. But we've got here, as you can see, we've got below period 5, we've got a value of 20,187.85 when there's no period amount. So we need to modify this if condition to state that if the period cell is equal to blank, then we don't want this cell to return any value. So what we'll do is we can go outside the function and then do if the period value is equal to nothing, in other words, if it's a blank, so we donate that by using 2 double quotation marks with no space in between. So if cell A11 is equal to blank, then give me a blank again. Otherwise, then we specify the if condition as normal, then we close the brackets at the end, we press enter, and then when we drag the formula down, it disappears. This just cleans up our table. Next, we need to identify how this total periodic loan repayment amount is split between principal and interest element. So let's start by calculating the interest component. So in the case where the payment type is 1, in other words, when we repay the loan at the start of each period, we know that the first repayment at the beginning of period 1 will not contain any interest element. So we need to specify an if function which incorporates this. So we'll do equals if the payment type is equal to 1, then the interest component will be 0. Otherwise, if the payment type is not equal to 1, in other words, if it's equal to 0, whereby we repay the loan at the end of each period, then we want there to be an interest component, and that will be equal to the total principal amount, which is outstanding at the beginning of the first period, and then we'll times that by the adjusted interest rate. And remember, because the interest component represents a cash outflow, because it's being included within our total repayment amount, that needs to be a negative value, so we'll times that by -1. And again, we specify the if blank condition at the beginning of the formula. This basically means that if the period cell is equal to a blank, in other words, there's no value contained within that cell, then we don't want the interest element cell to return any value. We want that to be a blank as well. So we'll do equals if the period cell is equal to a blank, then we want the interest element cell to return a blank. Otherwise, we display the if condition as normal, and then we close the parentheses, and then enter, and we get a 0 interest component within the first period. If we change the payment type to 0, you'll see that we have an interest component of 5,000. Let's change it back to 1. So next we want to work out the principal element in period 1. So that's going to be very simple. It'll just be equal to the total repayment amount in the first period minus the interest component. And then we press enter, and then we drag down the formula. And you can see there's an error, a value error message below the table. The reason why is because we forgot to specify the if blank condition at the start of the formula. So if the value in the period cell is equal to blank, then give me a blank, and then we close the parentheses, enter, and then we drag down the formula, and then that clears away that error message. And now we want to work out the interest component from period 2 all the way down to the end of the loan term. So we'll use the same formula for both a payment type of 1 and a payment type of 0. So the interest element in period 2 will be equal to the remaining principal amount at the end of period 1 times by the adjusted interest rate. Because we want to drag down the formula to the bottom of the table, let's fix the cell reference for the adjusted interest rate. Now we want to specify our if blank condition at the start of the formula. So if the value in the period cell is equal to a blank, then give me a blank, and then we close the parentheses, press enter. And I forgot one important thing, because the interest element represents a cash outflow, this needs to be a negative value, so let's times the adjusted rate by -1. We then press enter, and that gives us a negative value for our interest rate. And then if we sum these two together, the principal and interest, we get the total periodic payment amount of 20,187.85. Now we can drag down this formula. So as you can see, we've now got the right outstanding principal amount in the final period, period 5. We've got a figure of 10,000, which matches our balloon payment. Whereas if we compare it to the old table, which uses the Excel inbuilt financial functions, namely the PPMT, the PMT function, and the IPMT function, we've only got a figure of 9,523 outstanding principal balance in the last period, and that's not equal to 10,000, it's less than 10,000. So the table which we've built in this video is much better and far more accurate than the table which uses the Excel's inbuilt formula, and like I said earlier in this video, that's due to there being an error in the discount factor which the Excel functions use when calculating the repayment amount. And also, just to compare the two tables again, so if I change the payment type to 0, which means we're repaying the loan at the end of each period, and if I do the same thing on the old table which used the Excel inbuilt financial function and I change the payment type to 0, if we compare the values across the two tables, we can see it's exactly identical in every single cell within the table, which again confirms that the table which we built using these mathematical calculations and discount factors and present values, it gives us the right figures when building our loan amortization table. And if we change the payment type back to 1 so that the loan is repaid at the beginning of each period, and if we change some parameters, so if the repayment frequency is semi-annual, we can see that at the end of the loan term the remaining principal is 10,000, which is equal to our balloon payment. If we were to change the repayment frequency to monthly, we can see again at the end of the loan term the balloon payment is 10,000, and if we were to say, let's switch it back to annual, if we were to then change the balloon payment amount to 20,000, we can see that the remaining principal is 20,000, and if we were to say change the number of years in the loan term to say 8 years and change the interest to say 10%, we again can see that the remaining principal at the end is 20,000. So this is the most accurate model that you can build, and is probably better than actually using the Excel financial functions. So thank you guys for watching this video.